These are the solutions for the end of chapter homework problems for chapter 2. Number 1 says, look at the following set of 20 scores and place them in a frequency distribution table. In order to create a frequency distribution, we first consider the highest score and the lowest score. So I'm going to identify my highest X value and the lowest. So it looks like the highest is number 7 and lowest is 1. So I'm going to begin by listing my X values, starting with 7, counting down 6, 5, 4, 3, 2, 1. Okay, and even if any of these X values did not appear in the data set, let's say for example 4 was not part of our data set, we would still list it and then simply identify the frequency as being 0. Alright, so what we need to do is identify how often 7 occurred in our distribution. So if we look in the top row, we see that it occurred once and twice, so a frequency of 2. Now we're going to identify how often 6 occurred. So we have occurring once here, and then 2 times, and then a 3rd time. Okay, so it occurred 3 times. It's good to cross them out to make sure you don't double count, and there are ways for us to check our answers at the end, which I will demonstrate in just a minute. So 5, the top row does not appear. In the second one we have occurring once. 4, we have once here, and that's it. And then 3, we have once here, 2, 3, 4 times, so frequency of 4. And then 2, we have once, twice, let's see here, 3 times, 4, 5, and 6 as a frequency of 6. And then our last value, or X value of 1, we have 1, 2, and 3. Okay, so we have frequency of 2, 3, 1, 1, 4, 6, and 3. And a good way to ensure that you haven't left anything out is to recognize that the sum of frequencies is equal to n. So if you think of each frequency, if we're talking about individuals, and these are scores on a quiz, the X values are scores on a quiz. We had a sample of 20 individuals, 20 scores total. So each frequency represents one quiz score. So the summation of our frequency should equal the number of scores we began with. So if we take 2 plus 3, and then 1, 1, 4, 6, and 3. If we take the summation of that column, we have 10, 15, 16, 17, 18, 19, 20. So our sum of frequency is equal to 20. And that's a good point to check your work to ensure that none of these scores have been omitted, which is very easy to do. Alright, this is all that this problem asks us to do, but I'm going to take it one step further just to demonstrate a couple more skills that we learned in this chapter. And this is a good problem to do that with. So we were taught to calculate our proportions, or we can refer to as relative frequency. So our proportions again, the part of the whole, it's the same as relative frequency, and is equal to our frequency over n. Okay, so again, I'm calculating, I'll just make this column quite large so we can show all the work. So again, we want to know the proportion, or what we can then convert into the percentage, right? How often did we see this score of 7 occur in this distribution? So to calculate that, we would again take our frequency over n. So our frequency for the score of 7 is 2. So 2 over n, which is 20, gives us a proportion equal to 1.0. And then the next one, our frequency is 3 over 20, and that gives us a proportion of 0.15. Next one, 1 over 20, and we get 0.05. 1 over 20 again, 0.05. The next one, we have a frequency of 4 over 20, and that gives us a proportion of 0.20. 6 over 20, and we get a proportion of 0.3. Finally, 3 over 20 is equal to 0.15. Again, a proportion can be thought of as a fraction, right? What part of the whole is being expressed by that particular x value. So we can ensure that we haven't made any mistakes by taking the sum of our proportions. So what do you think the sum of our proportions should equal? So the 0.1 added to the 0.15, 0.05, if we're talking about this entire distribution. So again, this represents a portion of the whole. So if you said that the sum of our relative frequency should equal 1.0, you're correct. Because again, all of these scores represent the whole. And we're saying that the score of 7 occurring twice represents a proportion of 0.1 of the entire whole. The whole should equal 1.0. In terms of percentages, we would recognize that if we take the sum of the percentages, that should equal 100%. Okay, so that's a good place to check. You want to check your proportion values, take the summation, and it should yield a total of 1.00. Now let's convert these into percentages, and all we need to do is simply, one of two things: move the decimal over twice to the right and express it as a percentage, or multiply our proportion of 0.1 by 100 to get our percentage. So in this case, we're looking at 10%. So in other words, 10% of the distribution is represented by a score of 7, or in other words, 10 times, 10% of 100, right, represents the score of 7, or the score of 7 occurred 10% of the time. Next one, 15%, right? A score of 6 represents 15% of the distribution. Score of 5 represents 5% of the distribution. Score of 4 represents 5% of the distribution. A score of 3 represents 20% of the distribution. A score of 2 represents 30% of the distribution. And a score of 1 represents 15% of the distribution. So again, the sum of our percentages, let me erase that for a second. Our percentages should equal 100%. And if your proportion equaled 1.00, then you could feel pretty confident that the percentage should also be accurate of 100%. So again, if we were to, and I should erase this, I see a little mistake here. I wrote my decimal, and that is not correct. So this should be 15%, not 0.15%. All right, so again, this percentage column accounts for the whole entire distribution. So the summation of those percentages should represent 100% of the distribution of scores, and we were working with 20 scores total. Again, this problem didn't ask that we do these additional steps, but it was a good problem to take it a couple steps further to demonstrate some of the skills that we learned in this chapter. For the following problem, we're asked to look at this distribution, find each value requested for the distribution of scores. So A says, identify what n is equal to. Just as I illustrated in the previous problem, the summation of our frequency is equal to n. Again, you can think of the frequency as representing one person. If these are scores in a quiz, we would say that 2 individuals scored 5, 3 individuals scored 4, 5 individuals scored 3, so on and so forth. So if we were to take the summation of our frequency column, sum of frequency, that will identify what n is equal to. Okay, so we have 2 and 3, 5, plus 5 is 10, plus 1 more, and we get a total of 12. So that is the sum of frequency equivalent to our sample size n. N is equal to 12. We have 12 individuals in this data set, or 12 scores, I should say, total. The next asks B, the sum of x. Now, many of you are going to want to simply perform this given what is identified. So you want to go to your x column and take the summation of 5 plus 4 is 9, plus 1, 10, plus 3, 13, plus 2 more is 15. And you're going to want to put the sum of x is equal to 15. That's going to be your tendency because you are simply identifying the sum of x. But that would be incorrect, and the reason for that is because we have consolidated the data into a frequency table. And so if we just take the sum of x, we are assuming that each of those x values only occurred once. But we see here in this table that all with the exception of the values of 2 and 1, they had frequencies more than higher than 1. So again, don't make the mistake of just taking the sum of your x column. You have to take into consideration how often each of those x values occurred. So one way to approach this is to take your x value and multiply it by the frequency, right? So x of 5 occurred twice. So we take 5, right, and multiplied by, you know what, I'm going to rewrite that slightly differently so that it is a little easier to read. We have our x values, we have our f values. So let's create a column that says fx, a frequency multiplied by our x value. So we have 2 times 5 and we get 10, right? Then we have score of 4 occurring 3 times, and that yields 12. We have a score of 3 occurring 5 times, and that gives us 15. The next one, we have a score of 2 occurring once, so that's equal to 2, and finally a score of 1 occurring once. So again, now by taking our frequency and multiplying by our x value, we've accounted for the fact that these x values, with the exception of 2 and 1, occur more than once. So now if we were to take the sum of fx, right, all x values with their corresponding frequency, then we'll get the accurate answer for the sum of x. So if we take 10 plus 12 plus 15 plus 2 plus 1, we should get a summation of 40. Okay. Another way to think about this is if you were to stretch out, again, a frequency distribution consolidates information. If we were to stretch it out and write all of the values that occurred and write them every time they occurred, we would see this much longer list of scores. So for example, if I were to write 5 and it occurred twice, right? And then we have 4 occurring 3 times. And then we have 3 occurring 5 times. 3 occurring 5 times. 1, 2, 3, 4, and 5. And then we have 2 occurring ones and 1 occurring once. Okay, so we should have a total of 12 scores if I didn't leave anything out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 scores. And again, here, if we were to take the sum of x, right, that would also equal 40. But here it's okay to take the sum of x because I've accounted for every value that occurred more than once. So I wrote down 5 2 times. Well, this table up here that we have in the frequency distribution table, we've consolidated information. So these are 2 ways that you can approach this type of problem. Just don't make the mistake of summing up your x value and disregarding the frequency. Either stretch the distribution out, as I've done here, or use the consolidated table format to calculate your x values. So multiply your frequency times the x and then take the summation. All right, next we're asked to, so again we can write here the sum of x given those 2 processes that I just demonstrated is equal to 40. Finally, we're asked to calculate the sum of x squared. So given our order of operation, we recognize that first we have to take all of our x values and square them. So we'll do that. And then, just as we did with the previous process, recognize that each x value, with the exception of x equal to 2 and 1, they occur more than once. So let's just begin by taking our x values and then creating a column of our x values squared. Okay? And we have x values of 5, 4, 3, 2, and 1. And we're going to square those. 25, right? 5 squared is 25. 4 squared, 16. 3 squared, 9. 2 squared, 4. And 1 squared, 1. Okay? And now, given these values, we've identified that each x value has been squared, and then C in this problem asks that we take the sum of x squared. So again, don't make the mistake of simply taking the sum of this column here, the sum of x squared. Right? That would be incorrect because once again we have to recognize that these x values in most cases occurred more than once. So let's create a third column and we're going to call that f of x squared. Okay, so we have to again take into consideration this column. How often do those x values occur? So f, our frequency for our first value, is 2. So 2 times our x squared value, which is 25 in this case, is equal to 50. Okay, so our x value was 5. We squared it. It equaled 25. That score occurred twice, so 2 times 25 gives us 50. The next one, we have a score of 4. It's been squared to 16, and it occurred 3 times. Right? So we would take 3 times 16, and we get 48. Okay. Next, we have a score of 3 that's been squared, which is equal to 9, and that occurred 5 times. So we go 45. Score of 2 has been squared, equal to 4, and that occurred 1 time. So 4 times 1 is 4, and then finally a score of 1 squared is equal to 1, and it occurred, according to our frequency, 1 time. All right, now we can take the sum of fx squared, because again, in this final column, we've taken into account that all these scores have been squared. That was our second column, and then recognizing that in most cases, those scores occurred or had a frequency greater than 1. So we multiply that squared value by how often the score occurred. Taking the summation yields 148. So I got that by taking 50. If you enter that into your calculator, 50 plus 48 plus 45 plus 4 and plus 1, you should get a total of 148. So this is equal to 148. Okay, going on to the next problem. Actually, before I go on to the next problem, similar to what I did down at the bottom here, we can think of that process and apply it to what we just did. So again, given the squared value of the first score, 5 squared 25, it occurred twice. So another approach is to stretch all of the data out. So again, we would say that 25, right, occurred twice. So we would write it 2 times. And then the score, a squared score, 4 squared is 16, and 16 occurring 3 times. 16, 16, 16. The next score of 3 squared would be 9, and that occurred 5 times. So 1, 2, 3, 4, 5. And the next score of 2 was squared, which is equal to 4, and that had a frequency of 1, so 4 here. And then finally, a score of 1 squared is still 1, and it had a frequency of 1. So this would yield the sum of x squared using a slightly different process, a little more time consuming. From my perspective, this may make more sense to you, or a little easier to calculate. So if we were to take the sum of all of these numbers, again, we've stretched out the data, we should get the same of 148 if I haven't left any values out. So we can move on now to the next problem. In this next problem, we're asked to apply our skills that pertain to developing a group frequency table. So a frequency distribution helps us consolidate the information. A group frequency distribution table does the same, but consolidates information even further and creates a range of values that will be represented by a particular frequency. So we're going to construct a table where the width of our interval should equal, in the first one, 5. So the width is equal to 5. When we say the width, it's the same as when you'll see I. I is equal to 5, the class interval size. And we're going to use this data. The data is the same for A and B. And again, we're just constructing 2 different group frequency distributions, one with the I equal to 5 and the other I equal to 10. So we're going to begin by labeling our categories. So we're going to have our X values. And we're also going to identify our frequency. Okay. In order to start constructing our table, we need to adhere to the guidelines that I've placed here. So again, the guidelines are the group frequency table should have about approximately 10 class intervals. And when I mean class intervals, how many columns do you need to capture all of the data? The width of each interval should be relatively simple, a simple number to work with. So those include things like 2, 5, 10, and 20, because we're very accustomed to counting in multiples of 2, 5, 10, 20, 25, 50, 100. All of those would be reasonable, depending on how large of a data set you're working with. The bottom score in each class interval should be a multiple of the width, or multiple of I. In this case, it's 5. So you want to be counting by 5s, and I would take it one step further and say that it should be evenly divisible by 5. So you're either going to be counting 5, 10, 15, 20, 25. Notice that all of those numbers are evenly divisible by 5. And finally, number 4 says all intervals should be the same width. So we don't want one class interval with I is equal to 5, and the next one is 10, and the next one is 2. You have to be consistent in constructing your table. All right, so we're going to start on the higher end of our X values. We identified here in the problem that X equal to 52 is the highest value. So what we need to do is think about a range of scores where 52 would reside, and that the lower end of that range is a multiple of 5 and evenly divisible by 5. So again, 52 has to fall in this range of scores, and they should include 5 values. So I'll give you a second just to think about it, what value below it, a value below 52, that is a multiple 5 and evenly divisible by 5. So if you said 50, you're correct. So we begin with 50, and we take the range through 5 values. Now many of you are going to want to write 50 through 55 because you think you add 5 to 50, but that would not be correct. So let's erase that, because the range includes 5 values. So if we start, I'm going to write up here 50, 51, 52, 53, and 54. That is a total of 5 values. We have 50, 51, 52, 53, 54. So the range will incorporate 5 values, 5 x values. And again, that represents a size, or I value, class interval size, of 5. Okay, so again, just count it off. 50, 51, 52, 53, 54. Includes 5 values. All right, so we need to take it all the way down to the lowest class interval, which should include the lowest score of 17. So let's just count by 5s, moving our way down the left side, the lower end of each class interval. So it would be 45, 40, 35, 30, 25, 20, 15. And at this point, you should recognize that you don't need to go any further, because our lowest number in our distribution is 17. So if we again go out 5 values, this would be 15 through 19, 20 through 24, 25 through 29, 30 through 34, 35 through 39, 40 through 44, 45 through, should be a 4, 49. Notice that where one ends, the next picks up. So we have a range of 15 through 19, and then 20 through 24, so on and so forth. So again, this left column of numbers, 50, 45, 40, 35, are all multiples of 5 and also evenly divisible 5. Each class interval is equal in size. They each contain a range of 5 values. So the next part is the little bit more tedious part of this process, and I recommend that you do the following. That if you just cross off the values in your distribution, the scores, and then tally the frequency, that will hopefully minimize any errors that you might commit. So a value of 44 would fit into this category. So we just tally one. A value of 19 fits here. 23 would fit here. 17 here. 25, 47, 32, 26, 25, 30, 18, 24, 49, 51, 24, 19, 43, 27, 34, 18, 52, 18, 36, and 25. Okay, so if I've accounted for everything properly, and hopefully this is accurate, again, you can imagine that it's very easy to make mistakes, but again, if you tally off the numbers that you have accounted for and record the frequency, you're more likely to get an accurate answer. So let's write the numeric values that represent these tally scores. So we have 2, 2, 2, 1, 3, 5, 3, and 6. So this column here where you see the tallies would not be an appropriate representation. You would want to see these numeric values, but I did that step just to show you how you can add that process to make it a little easier to account for all the scores in your distribution. So here what we're saying is if you take this second 2, that 2 scores fall within the range of 45 to 49. This last column, we have a frequency of 6, so all we're saying is that 6 of the total number of scores fall into a range of 15 to 19. So again, this is the complete process of constructing a group frequency distribution that when we adhere to the guidelines that are presented on page 42. Again, that first point being made is that the group frequency table should have approximately 10 intervals. That means how many rows or columns we need to account for all of the data. So there's 3 and 4, 5, 6, 7, and 8. Again, it's not a precise calculation. These are estimates, guidelines that we prefer to have a table that has at minimum 10 class intervals. But we recognize that it's never going to be perfect, but you want to get as close to 10 as possible. 10 gives us just the right amount of numbers where we're not consolidating information so much that we lose patterns, right? Or the opposite effect, that we have so many class intervals that there really is no purpose of constructing a group frequency table. The more class intervals we have, the longer the distribution of values becomes in that particular table, and it kind of defeats the purpose. So we want a happy medium around 10, close to it. 8 is close enough where it produces a pretty nice distribution. Let me just give you some other equations that aren't necessarily in the book, but I find kind of helpful. If you take the range of scores, and the text does talk about this, which is your high score minus your low score plus 1. If we take our high score of 52 minus 17 plus 1, we get 36. Okay? And if you take your range and divide by, so our range divide by our eye size, so 36 divided by our I, which is 5. So in your calculators, if you divide 36 by 5, we get 7.2. And what I should have written here, instead of an equal, it should be more of an approximately equal to. So approximately equal to 7.2. And what I've just calculated is how many columns I'm going to need to capture all of the information. 7.2 is a mathematical calculation. Given that I've already constructed this table, I find that I actually needed 8, right? So you can't have a fraction of a column here. So if we round that up to the next whole number, we would get 8 columns. Another equation that might be of help for you to kind of reconcile all of this in your head and make sense of it or check your answers. If you take the range of scores, divide by number of CIs. CI stands for class intervals. Okay, so if we take our range, which was 36, and going back to the guidelines, if we want 10 as an ideal number of class intervals, right, we get 3.6. And what I just calculated is the estimated interval size. So going back to the guidelines, it says that the width of each interval should be a relatively simple number. Obviously 3.6 is not a simple number. So we look at the options, what's recommended, 2, 5, 10, 20, 25, 50, 100. So this number is a good estimate of how we could produce 10 class intervals, which is the ideal situation for constructing a group frequency table. So we would round up, okay, so an I equal to, or approximately equal to, 5, right? If we take 3.6, round up to the nearest whole number, which is one of the recommended I values, again going back to point number 2, 2, 5, 10, or 20. 3.6 is closer to 5 than it is to 2, so we would conclude that if we were to use an I size of 5, we're going to generate a table that has approximately 10 class intervals, right, which meets the guidelines that were presented to us. So these calculations, again, aren't necessarily presented in the textbook, but I find that doing these estimations will kind of help you check your answers in terms of the guidelines that have been presented here. One more thing before I go on to B is a good way to check to ensure that you didn't omit any of the scores in your distribution is simply to take the sum, excuse me, let me go back to make that a 6. Take the sum of your frequency and that will equal n. So if we add this column here, 2 plus 2 plus 2 plus 1, 3, 5, 3, and 6. If you enter all that into a calculator, we should get the sum of our frequencies is equal to 24. And you want to make sure that that's how many scores you started with. So over here, right here, these are all the scores that we originally began with. And if we take, let's see here, we have 3 columns, and then we have 8 scores. 3 times 8, whoops, times 8, excuse me, is equal to 24. So this is a good way to check before you go on to make sure that all the scores have been accounted for. All right, next I'm going to erase all of this and use the data set, same data set to construct a group frequency distribution table using I equal to 10. Okay, so I'm going to erase all of this and start all over. And you should note the difference of the look and also adherence to the guidelines. We should talk a little bit at the end about which table meets the guidelines better. Okay, so this next one we're going to use I's equal to 10. So again, we're going to draw our table with our x values represented and our frequency, don't need a line that long. All right, so again, our highest number is 52. We have I is equal to 10. Okay, so just as we did with the last one, we want to look at the high number of 52. Think of a value less than 52 that is a multiple of 10, evenly divisible by 10, and carry that out 10 values up, right, to create a range of 10 scores that includes the score of 52. So again, think of a value that's less than 52, that's a multiple of 10, and evenly divisible by 10. All right, if you came up with 50, again, here, let's see here, 50. Right, that would be correct. We're going to have a range of 10 values. So again, don't make the mistake of saying 50 to 60. I'm just going to make this a little clearer here. To 59, right? So I had written up here through 54. So if we go 55, 55, 56, 57, 58, and 59. If we count all of those, we should represent or see the representation of 10 values. Okay, so it's 50 to 59. We're just going to go 10 less. 40, 49, 30 to 39, 20 to 29, and 10 to 19. We can stop there because the lowest number in our distribution of scores is 17. So that 17 would fall into this lowest category here. One thing I neglected to mention in the previous problem or example was, in addition to these guidelines, you should recognize that your high score must be accounted for in your highest class interval, and your lowest score must be accounted for in your lowest class interval. In other words, you wouldn't want to go one interval below that and say 0 through 9. If you were to do that, we would look at our data and check to see if the score of 0 was illustrated, or any score from 0 to 9, and we would conclude that there aren't any scores in that range, and therefore our frequency would be 0, and that would be incorrect. You never want frequency of 0 represented in your lowest or your highest class interval, so make sure that you stop where you need to. It will most likely become evident if you do make a mistake and you record a frequency of 0. We could have 0 in any of the middle class ranges, but definitely not at the lowest class range or at the highest class range. All right, so just as we did in the previous example, we're just going to go through these X values and tally them in the appropriate range. So 44 is going to be our first value, and it fits here. 19 fits here. 23, 17, 25, 47, 32, 26, 25, 30, 18, 24, 49, 51, 24, 19, 43, 27, 34, 18, 52, 18, 36, and finally 25. Okay, hopefully this is all correct, and so the numeric interpretation would be 2, 4, 4, 8, and 6. Okay, so again, just as I said in the previous example, you want to take the sum of your frequency here. Sum of f is equal to, if we take this, the sum of this column, 2, 4, 8, and 6, we get 24. So again, just confirming that we've accounted for all of the scores in our distribution, and we are good. In comparison to the previous frequency distribution table, which do you think meets the guidelines better? So again, going back to the guidelines on page 42 that I've stated here in this problem. The first one stating that ideally we want 10 class intervals. And in this case, if we take this out here, we have 1, 2, 3, 4, and 5. So again, even though in the previous example we only had 8, it was closer to 10, and that's the ideal. So the approximate numbers here give us a sense as to whether or not we're meeting the guidelines or not. In this case, we would conclude that the previous process of using I equal to 5 is a better implementation of the guidelines than in this case of using I equal to 10, because as a result here we've consolidated the data too much, where we start to lose some patterns, and we as a result aren't adhering to that very first guideline, so that we want at minimum, or I should say approximate number of class intervals to equal 10. In this case this gave us 5. So if we were to compare the two, this one would not be preferred, and the I value of 5 would be a better option. So hopefully you see the relationship that as I decreases, the smaller I value is going to yield larger number of class intervals. So as I decreases, we need more class intervals. Okay, obviously the reverse is true. As I increases, we need fewer class intervals. And I bring this up because you can do those calculations like I showed in the previous example of taking your range and dividing by the ideal number of class intervals needed, which in this case is 10, and what kind of I is that going to yield, and do these calculations prior to constructing your table, prior to identifying the ideal I size. So smaller I values need a larger number of class intervals. Larger I value consolidates the information more, and you're going to need less class intervals. Okay, so that's it for constructing our group frequency distribution when I is given. Now for your purposes of your APLIA homework, this information will be given to you. In the next problem, we'll just look at high scores and low scores and try to identify what the ideal I value would be to meet that first criteria listed here in the guidelines. Okay, similar to the last problem, we're going to work with the concepts of a group frequency distribution, again keeping in mind the guidelines that were presented on page 42. So here we're just given the range of scores that include the high score and the low score for 3 particular distributions. And what we're asked to do is to identify the ideal I, or interval width, that would produce a distribution, a group frequency distribution with the ideal number of class intervals. And again, remember that approximately we want 10, something close to 10 class intervals. So we are first given an A. let's see, we have our high score. High score is equal to 41, and our low score is equal to 8. So let's calculate the range of scores that we are working with. We have our high score minus the low score plus 1. This is how we're told to calculate the range. And the plus 1 comes from just how I demonstrated in the last example where we had a range of 50 to 54. So we have 50, 51, 52, 53, 54. We have, it appears like we have 4 numbers in that range, but if we count them out, we recognize there are 5, and that's where the 1, adding the 1 comes in. So if we have 41 minus 8 plus 1, okay, if you take that into your, put that into your calculators, again, we have 41 minus 8 plus 1, and we should get 34, okay? The range of scores represent 34 values. And I'm going to just demonstrate different I values, kind of a trial and error process. And once you start to see what I'm doing, I think it'll be easier for you to do it on your own. But I'm going to just pick of the ideal I widths that were presented in the guidelines, such as 2, 5, 10. I'm going to start there and then see which of those yields the ideal number of class intervals. Again, I'm shooting for something close to 10. It's not going to be exactly 10, but approximately 10. So if I begin with I equal to 10, we already know, based on the previous example, the larger the width size of the class interval, the larger I is, the fewer class intervals I'm going to need. So you should probably already get the sense of whether or not 10 is going to work. So if we want to find out or approximate the number of class intervals needed if we use I equal to 10, let's take our range, right, and divide by our I. And this will give us approximate number of intervals. Again, this is the number we hope to be close to 10, as close as possible. So if we replace our variables, we say that our range is equal to 34. We're going to use I equal to 10. 34 divided by 10 gives us 3.4. And what I'm calculating, again, is an approximation of how many intervals we need. So if we use a class interval size of 10, then that's going to help us construct a table where we're going to have approximately 3.4 of class intervals. Obviously, you can't have a fraction of an interval, so most likely it's going to yield 4 class intervals. Does it meet the guideline? No, the guideline was 10. So let's try I equal to 5. Okay, so again, we're going to take our range, divide by I, and that's going to yield an approximate number of intervals that we need. Okay, and again, it's an approximation. We take the range 34, right, divide by 5. So in your calculators, 34 divided by 5, we get 6.8. Okay, so again, definitely better than I equal to 10, because I equal to 10 only gave us a scenario where we would need at minimum 4 class intervals. I'm rounding up to the next whole number. Here we're going to need approximately 7 class intervals, which is closer to 10. So 5 is looking good. But before we make our decision, let's try 2. I equal to 2. So again, take our range, divide by our I to get an approximate number of intervals needed. Okay, so again, it's 34, and divide by 2. And we get an approximate number of 17. Okay, so again, if we go back and analyze the differences, we can conclude too few, right? This is too many, right? Well over the ideal of 10. And we would conclude that this would be just right, that this would yield approximately 7 class intervals. And as a result, we conclude that I equal to 5, right, results in approximately 7 class intervals. And when comparing the other potential I sizes, this would be the best. It's closest to 10, right? Given I equal to 10, that only gave us 3.4, 4 intervals needed. And then I equal to 2, it yields a distribution, a frequency distribution with 17 class intervals, which is far too many, more than is what is recommended. So we conclude in this one that I equal to 5 is the ideal number. All right, going on to the next one. All right, so we're going to now tackle 7b, and to do so I'm going to give myself some room here, so I'm going to erase what we just did. Follow the same process though, and apply this trial and error scenario to identify the ideal I size that's going to yield something close to 10 class intervals. And we'll start with calculating the range. Okay, so we have B. We have our high score equal to 33. And our low score equal to 16. So our range is equal to high score minus low score plus 1. It's equal to 33 minus 16 plus 1. So if you enter that into your calculators, you have 33 minus 16 plus 1, and we should get a range of 18. Okay, so we have 18 scores represented in this particular distribution. Again, we don't have all those scores, we're just given the high score and the low score. And now we're going to take our I values, again the ideal, 2, 5, and 10, and plug them into the equations I've just shown you to assess which is the best I size that's going to yield something close to 10 class intervals. For many of you, you probably can already see it. The math is pretty easy, and you probably already know the answer, but nonetheless, let's go through all the steps. So let's consider I equal to 10. Again, we know the larger I is, the fewer class intervals we're going to require. So if we take our range and divide by our I, we're going to get an approximate number of intervals needed. Okay, and so if we take, in this case, 18, divide by 10, we get 1.8. Obviously, far too few class intervals to meet that criteria of 10. We can do 5 next, and I'm sure you can see where we're going here. Range divided by I is equal to number of intervals. So we have 18 divided by 5, and I believe that's 3.6. It's 3.6. Again, better than I equal to 10, but still not enough intervals. Let's try 2. Our range divided by I gives us approximate number of intervals. So we have 18 divided by 2, and we get 9. Again, too few, and this would be just right. Okay, so I equal to 2 gives us approximately 9 intervals. Again, that's how many columns you need to capture all of the data, and that would be the ideal. So we can, again, see the pattern that as I is larger, we have fewer class intervals. As I decreases, it increases how many intervals we need to capture all of the data. And our goal is to produce a frequency table that has somewhere close to 10 class intervals. So 9 would be the ideal. In most cases, you're not going to need to do the trial and error every time in this manner, but seeing it like this over and over again will help you do it quickly in your head to come up with the correct answer. I'm going to do one last one. Okay, so this is the last one. See, I have my blank slate here. Erased everything. So I have my high score equal to 98, my low score equal to 26, my range is equal to high score minus low score plus 1. We get 98 minus 26 plus 1. So again, in your calculators, if you enter 98 minus 26 plus 1 is equal to 73. Our task is to find the ideal eye size and trying to meet that criteria of using those simple numbers of 2, 5, and 10. In addition to that, producing a group frequency table that has approximately 10 class intervals to capture all the data. So just as we've done before, we're going to start with this trial and error process, I equal to 10. If we take our range, divide by I, we'll get an approximate number of intervals. And so if we take a range of 73, divide by 10, we get 7.3. So again, we can't have a fraction of intervals, so technically it would be 8 intervals that would be required. Next one, 5 as an option. Our range divided by I, we get 73. Excuse me, that's going to yield approximate number of intervals. So we have 73 divided by 5, and we get a larger number, right? We're dividing by a smaller number that's going to yield a larger quotient of 14.6. Going back to our guidelines, too many. As you can imagine, if we decrease it, it's just going to be the same, where we have a quotient that's much larger, dividing by a smaller number. Approximate number of intervals. 73 divided by 2, and we get quite large quotient of 36.5. And very easily we can assess which is the ideal eye size. So too many class intervals, too many, far too many, we would say. And this would be ideal. So I equal to 10 gives us approximately 8, rounding up, class intervals. And that would be the ideal eye size for that data set where the high score is 98 and the low score is 26. Okay, so again, as I've said before, you probably don't have to do this trial and error in this manner every time. A quick assessment of what the range is divided by, a larger number such as 10 versus 2, you will quickly see the pattern and be able to determine and assess what the ideal eye size will be. Okay, number 9. Describe the difference in appearance between a bar graph and a histogram and identify the circumstances in which each type of graph is used. So from our reading, we've learned that a bar graph is applicable to nominal and ordinal data. Okay, so again, reviewing what we learned in Chapter 1, nominal named categories and ordinal are categories ranked in order from highest to lowest. And a histogram, which is technically also a bar graph but represented slightly differently, histogram is applicable to data that includes interval and ratio. So quantitative data versus qualitative data for a bar graph. So first, we would know that a bar graph is used when we are working with nominal data or ordinal data. Histogram we would use if we're working with quantitative data such as interval and ratio. And a quick little example of a bar graph. Let's say we're looking at the majors represented in this class. And this is their frequency, although that doesn't look so hot, so we'll change this frequency. And if we just put values here, 5, 10, 15, and then our majors, so let's say we have Soc and Psych, criminal justice, nursing, okay, just to name a few. And the height of each bar, so sociology majors, let's say there are 7 of you. Then psych majors usually make up the largest portion of our class. Okay, criminal justice, usually a fair amount, similar to sociology. And nursing, we tend to get quite a few nursing majors. So notice the bars adjacent to each other, there's space in between. And the reason is that Soc is distinctly different from psychology, and psychology distinctly different from criminal justice, and similarly from nursing. So they need their distinct categories visually represented. Again, the height is representing how many of those categories we see in the larger group. Okay, so, and again, in this case, I would ask, is this nominal ordinal data? So again, it's a named category. It's a major, and they're named categories, and we cannot rank them. So it would be an example of nominal data because they're just named categories. I cannot objectively say one major is better than the other. Subjectively, sure. I'm a sociologist, so I would put that as the best major, but objectively we can't rank them. So they would all be considered equivalent. Okay, a histogram is also a bar graph, but the representation visually is slightly different. So let's say we're again talking about frequency and the variable down here, age of children in a particular population. I'm not sure which population, but let's just put this again on our ordinate, 5, 10, 15. And then down here on our x-axis, on the abscissa, we're going to write our numeric values. So not starting at 0, but we'll start at 4.5, 5, 5.5, 6, 6.5, 7, 7.5. Okay, so the 0.5 numbers are, as from our reading, represent the real limits within the range. The whole numbers are kind of in the center. So, you know, if we're talking about children that are ages 4.5 to 5.5, let's say there are 10 of those individuals. Okay, so in the middle, the midpoint is actually the whole number. So sometimes, especially children, not adults so much, like to indicate, you know, they're 5.5 or 5 and 3 months, whatever it may be. They tend to like to report their ages in fractions. Age is a ratio scale of measurement. It's also a continuous variable where we can break it into smaller pieces. So notice that where 5.5 leaves off, the next range picks up. So let's say we have in this next category 15 individuals from ages 5.5 to 6.5. Again, the whole number in the center representing the midpoint of that range. And then the next one, let's say there are 5 individuals from 6.5 to 7.5. Okay, some of you may be wondering, well, where does the 5.5 go? Normally you round up into the next interval. But anyway, what I want to illustrate here, these are the real limits that we would see with a continuous variable. Again, we can only construct real limits when we were working with quantitative data. And again, where one interval stops, the next begins. For example, 4.5 to 5.5. 5.5 to 6.5, 6.5 to 7.5. So notice visually the difference in representation. These bars are continuous. They bleed right into each other. So where one leaves off, the next one starts. And that's different from what we saw on the bar graph, where they have their distinct categories and therefore their spaces in between those adjacent bars, because one category does not bleed into the other. But numerically speaking, on this number line, they do bleed in together, meaning that it's continuous. So again, when you're asked a question of what kind of what kind of graph is most appropriate, think back to what kind of data you're working with, and identify the scale of measurement, and then that will most likely determine what type of graph is appropriate. On a side note, if you can use a histogram, you can also use a polygon. So a polygon applies to data that is represented in an interval scale or ratio scale. So you can think of them as synonymous with one another, that if you're going to use a histogram, a polygon would be just as good. So they kind of apply to the same kind of data situations. Visually, a polygon, as we learned, would be a line graph. I'm just going to go right over here, and we would connect those values, right? And then for it to be constructed accurately, we always have to bring it down to the abscissa, right, to the next value. So in other words, they're equal to one another. It's just a different representation visually.